We got lucky, kind of, that the derivative wound up including u itself. And now I can rewrite the integral, and everything will be in terms of u. So what will this new integral be? This is e to the u times dx, but what's dx? 2u du. Now pull that 2 out, and let's write it in this order. 2 and then integral u e to the u du. You'll follow? Now, when you look at this, you should be thinking integration by parts. Because if I choose this to be my, if I choose this to be my u, then the derivative of it over here is going to be 1, right? And if I choose this to be my dv, then the antiderivative I can take, right? So I'm going to be able to reduce that power on that u down and make it go away. The only issue is that I've already used u. So that means I'm going to make up a table here. And now my table, I can't use u. So I'm going to use my own variable. I get to make it up. You get to make it up. You can use whatever letter you want. I'm going to use w. This I can still call dv. So now your whole ultraviolet minus voodoo goes away. Okay, you can't use that little acronym anymore. But that's why I use a table, because I know my new integral is this times this, right? Minus the integral of the diagonal, regardless of what I call these things. Understand? Yes? Okay, so what's w going to be for me? What am I going to use for my w? U. And what's my dv going to be? Are you trying to come up with a little saying?
Yeah.
Ultraviolet, whatever.
Waffles and
Yeah. Okay, so that all right? Go ahead and finish off the table. This is dw is du, and then v is e to the u. I told you how in the differential equations class I'm doing the solutions, and I'm having to do this a lot, right? I mentioned that last class?
Yeah.
When I do integration by parts, when I do it, I don't even label the things. I would just put like u here, du, e to the u, and then e to the u du here. That's the way I do it. And then I just go, it's these two times, these two multiplied minus the integral of these two. I don't even call them anything anymore. But that's because, you know what I'm saying? After you get comfortable enough, you don't need to label things. But for here, we need formulas to get us started, first steps. Okay, here we go. This integral becomes, don't forget that 2 out there. That 2 is important, isn't it? It's 2, and then everything that the integration by parts formula provides us, which would be this times this, right? Across. So u, e to the u, minus a little bit of a space in here, integral. Do I have any constants to pull out?
No.
The diagonal does not have any constants. So it's just going to be e to the u du. And I really like to see this, right? Because the antiderivative e to the u is itself. So we get 2 u e to the u minus e to the u. And then at the end of the day, I'll have a plus c out here somewhere. And we can distribute, if you want, we can distribute the u through, or the 2 through. And we're almost there. What's the last step here? You got to replace u with what it was, right? What was u? Root x. So this is 2 root x e to the root x minus 2e to the root x plus c. Could we check it? I'm sure we could, and I'm sure it would work. So we have to do a substitution first.
You wouldn't have factored that into 1 e to the u?
if I was going to take the derivative, I would have factored out an e to the u. I would have left this 2 out here and just brought the e to the u out and left that as u minus 1 inside. But it's all the same at the end. Okay. Yes?
What are generally some triggers that would tell us to do substitution for?
On this one, there's really nothing. Who said that? Yeah, there's really nothing that's going to trigger you other than other things aren't working. So look, I wanted us to come back and look at this. Could we at this point say that when we look at this, that you're probably thinking integration by parts? Would that be safe? Because nothing else that we have appears that it would work here. Yes or no? Yeah? Okay, so let's try integration by parts without a substitution first. If I did that, I would have to pick a u and a dv. So we only have one choice here. dx has to go here, and this has to be e to the root x. You see that? That has to. This is kind of like that arc sine problem. And then we have to just follow through. This is going to be du equals e to the root x times 1 over 2 root x, chain rule, times dx, right? The antiderivative this way is going to be what? X? Just x? Okay? I think this actually might work. So the new integral is going to be multiply across x e to the root x, yes? And then minus a little bit of a space in case I have any constants. Do I have constants? 1/2?
Yeah.
I can pull this 1/2 out, can't I? I have 1/2, and then I have e to the root x times x over root x, which is, what's x divided by root x? X over root x is root x times root x. That's x, right? Over root x. Okay, so root x, x over root x is just root x. So now we're here. And you look at this integral, and what do you want to do with it? Maybe integration by parts again, but what are you going to use for u? You want to use that for u, and then you're going to integrate that? Can't do that, right? Right? If I use this for u and this for dv, I can't integrate that because that's the original freaking problem, right? So I know I'm not going to be able to do that. So this would have to be the dv, and then that would have to be your u. And then you run through it again, what you're going to realize is it's going to just start getting uglier and uglier, right? So to answer your question, like this is what makes this so difficult, okay? It's not like how one where you just have a formula and you just follow a procedure. It comes with experience and practice. That you start looking at it and you're like, okay, I know right now that a substitution is worth a shot first. And so you crank it out and you hope for the best. But it's just repetition, 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 problem recognition. I don't know if that helps, but I cannot give you like cookie cutter, like boxed, pre-made answers for these things because they're all just so different. Every problem is unique.
Can we try U sub on that one again or no? It wouldn't get anywhere.
If we did U sub here, I think we'd get there.
Because like you have the root x on top.
Yeah, it would most likely get us there. I don't want to because we're already one iteration into, we're already in an integration by parts right now. So doing a substitution now, I may as well have done it at the beginning if I'm going to do it, right? All right. How about this one? I'm going to put a star next to this one because you are allowed to put this into your formula sheet. You know the formula sheets you can bring to the tests? Okay, I never allow you to write on those formula sheets like your own little formulas. This one you can put in here. Put in there. I do not believe it's on the formula sheet. We all know what the antiderivative of e to the x is, right? It's itself. But what's the antiderivative of natural log x? We know the derivative of it is 1 over x, but what's its antiderivative? So what are we going to do? Integration by parts, probably, right? Well, if you do that, you're going to have to choose something to be u and something to be dv. So what do you got? Natural log x has to be the u, right? And the dv has to be the dx. So I think we can handle this. What's the derivative of natural log x? 1 over x. Okay, so this part's not too bad. This is 1 over x dx. Oh, and v is just x. Holy crap, look at the diagonal. 1 over x times x, right? That's just 1. Okay, so look, this is going to be ultraviolet, right? These two multiplied. X ln x minus a little bit of a space in case we have a constant, which we don't. And then is it okay for me to go ahead and just, you realize that right there is just going to be 1 dx? 1 dx. What's the antiderivative of 1? X. So you just get x ln x minus x plus a constant. That's it. That's the antiderivative of natural log of x. Just to verify, that's a product. So product rule would say derivative of that, which is 1 times this, plus derivative of natural log of x, which is 1 over x, times this one, x, minus the derivative of x, which is 1. And this right here is 1. So you get 1 minus 1 is 0, and you get natural log of x. So it works. So feel free to use that. How are we doing on time? Got a little 15 minutes. Reduction formula. Last one. You're allowed to have formulas on your test, right? But only certain ones. And if you were to look into the back of the book on reference page 9, which is not included in your formula sheets, you will see this formula. It's formula number 73. And it says, the integral of sine to the n of u du is equal to negative 1 over n sine to the n minus 1 of u, hold on, cosine of u, and then plus n minus 1 over n integral of sine to the n minus 2 of u du. That's what formula number 73 says. So let me show you how the formula works. If I wanted to do the antiderivative of sine to the 6th power of x dx, then n is 6, right? And then all I do is just plug it into this formula. So it would become negative 1 over 6 sine to what power? 6 minus 1 is 5 of x cosine of x plus 5 over 6 integral of sine to the fourth x dx. Okay? And then what you would do is you would go figure out what sine to the fourth x dx is. That integral, and you'd reuse this formula again. So what's in that orange box would become negative 1 over 4 sine to the third x cosine x plus 3/4 integral sine to the second power this time, right? So that would all go in right there for the orange. And then that other integral that was sine squared now, you would use this formula again. So you see how it'd be like the formula within the formula within the formula?
Keep doing that over and over.
Until you get it down to sine to the 0, which would just be 1. So you, at the very end, you'd have an integral, and that integral would be antiderivative of dx, which would be 1. So you would finally get it. They call these reduction formulas because what they do is they allow you to reduce your power down, just reusing the formula over and over and over. So you see that? You could handle this theoretically. If I made this sine to the sine x to the 60th power, you could use this formula over and over and over and over and over until you get it down to, you know, the power all the way down. Does that make sense?
So the answer would be like a page long?
It would be a page long. Yes, it would be tremendous. But the formula works, okay? I mean, it does work. It's helpful. It's helpful before we had computers, all right? So there are actually, I've seen entire books, like entire textbooks this big with just integral formulas for all these different special types of integrals, all right? So what I'd like to do in the last 10 minutes here is I would like to come up with how they got this formula, all right? Because it looks crazy, doesn't it? And it all starts back here at this problem. Now I'm going to use x instead of u. So our formula, when I'm done, we better have this with all our u's replaced with x's, all right? And before I get into this, everybody was able to pick up their stuff? They're, okay. What is for homework this weekend? Integration by parts. I have to imagine that the homework, my homework solution videos for this is multiple hours long. I can only assume that if I did like 30-something problems, that it took me a few hours to do it. So I would anticipate it taking you quite some time. But it's essential that you get this topic down because you're going to be tested on it a week from today. And the test that we have, right, it is a week from today? That test that we have is, yeah, I'm going to ask you to take some derivatives, you know, hyperbolic and, you know, arc whatever. But this class is not about derivatives. This is about integration. So you need to be focusing heavily on the basic stuff like, you know, powers, but more u substitution and integration by parts. You've got to be ready to roll next week with that. All right? All right, so you're going to have a good weekend. It's going to be raining, I think. So you just, you know, coop up and, you know. All right, let's try and get this reduction formula. This is our goal, okay? This is our goal. See if we can get it. And I actually, now that I'm looking at it, have kind of forgotten how to do it. But, no, I can get it. Hold on. We're going to do integration by parts. Okay? We're going to do integration by parts. But the first thing I want to do is, I want to rewrite this as sine to the n minus 1 of x times sine of x dx. So all I'm doing, if that makes sense, is like if this was sine to the 6th power, I'm writing it as sine to the 5th times sine. Yes? Okay. Now if I do it that way, then I have a product and I can choose one of these to be u and one of these to be dv, right? Agreed? So what I'm going to do is I'm going to let u be equal to the sine to the n minus 1 of x. And my dv, I'm going to let that be cosine x dx. I don't know if y'all, I doubt anyone can see this, but I actually did not remember how to do this, but I looked at the answer, and the answer revealed what I had to do. Because this is ultraviolet, and then this is your minus voodoo. And ultraviolet right here, I know that this is V, and this is U. So that told me, if this is V, then dV had to be, right? Sine. Oh, why did I put cosine here? Sorry. Sine. Yeah. Did y'all saw that, right? Y'all were wondering where the hell that came from? Okay, sorry. So this had to be cosine, which means dV had to be sine in some way, right? Okay. All right. Let's keep going over here. Forget that. All right. If I'm going to, let's do the antiderivative. I think this one's easier. Okay. Let's go up with this. So if I go up with this, the antiderivative of sine is negative cosine of x. Good. All right. Now, this part right here, be careful with. Du. So think about this. If it was sine to the 6th power, the derivative would be 6 coming out first, and then sine to the 5th power. And then you would take the derivative of sine. So chain rule. So if I do chain rule here, what's the derivative of sine to the n minus 1 power? What comes out? N minus 1 comes out. Then I'd have sine to what power? N minus 1 again, which is n minus 2 power of x. Make sense? And then the derivative of sine, which is cosine x dx. That okay?
Yeah.
All right. I mean, that's what it is. So here's where we are. We know that this integral will be equal to ultraviolet. What's ultraviolet? These two multiplied. Negative sine to the n minus 1. I don't know. Sometimes I'm putting it in parentheses. Sometimes I'm not. I don't know why I'm doing that. Okay, that's the first part. And then minus, with a little bit of a space, this time a big space, what constants can come out? This negative can come out, and the n minus 1 can come out. So why do I make it plus n minus 1? Okay, like that. You have to write it in parentheses. And then what's inside here? Sine to the n minus 2, yes? X, and then what? Cosine squared x dx. Oh, do you follow? Because you're doing the diagonal here, so it's cosine and cosine, right? And so we look over at this formula that we're trying to get to, and we go, what? Like we're kind of close, but not really. Like, do we have a sine n minus 1 and then cosine? We do have that, right? But this integral, look at the integral here. Sine n minus 2x. I have that, right? But what the heck with the cosine squared, right? So now the next step is I want everyone to remember that that really means 1 minus sine squared x, right? That's a Pythagorean identity. That's cosine squared. So what would happen if I took this and I distributed it through to both of those? What would my new integral be? So I'm going to have to write this. This negative sine to the n minus 1 of x cosine x. What you're looking at up here right now, everyone, this is what a bonus problem would be on a test, okay? Okay, here we go. Now this integral, now what happens when I distribute? This times 1 would just be itself, right? So I'm going to have two terms here. Sine to the n minus 2 of x, and then minus, and then when I distribute this to this, what happens there? What happens there? Sine to what power? N. Sine to the n, because you're doing sine to the n minus 2 times sine squared, so you add the exponents. N minus 2 plus 2 is sine to the n. So this is sine to the n, right, of x. And we're done there, right? Dx. Okay. So let's recap where we are. The original problem, right here, this original integral right there, is equal to negative sine to the n minus 1 of x cosine of x, almost out of time, plus n minus 1 integral sine to the n minus 2 of x minus, dx, minus n minus 1 integral of sine to the n of x dx. What happened here? What did I just do? I had two terms here, right? So I did the integral of each one separately, and I distributed the n minus 1 to each of them. So I have n minus 1 in front of this integral. That's here. And then I have n minus 1 in front of this integral with the minus sign, right? That's right here. Now, do you see that this and this are the same? You see they're the same? So do what we did when we had that rabbit out of the hat. If I have minus n minus 1 of these, I can add n minus 1 of these integrals to both sides. I realize I've lost many of you here, but that's why it's a bonus type problem. Okay, so I'm adding that. It goes away here. And what do I get here? If I have one of these, and I'm adding n minus 1 of these, how many of them will I have? If I have n minus 1 of them, and I'm adding one of them, how many will I have? N of them, right? N of them. So I have n integrals of sine to the n x dx equals negative sine to the n minus 1 of x cosine of x plus n minus 1 integral sine to the n minus 2 of x dx. That's where I am. And then what do I do at this point? Divide by n. Divide by n. So if I divide this by n, I'll divide this by n right here, and I'll divide this by n, which will give me negative 1 over n. And was that the formula?
Yeah.
It was. That's how we create reduction formulas. All right, have a lovely weekend. I'll take attendance today off of the quiz. So if you didn't take the quiz but you were here, you might want to just let me know so I don't count you absent.
Hey, before everybody leaves, I was going to talk about this on Monday, but so I had talked to, I don't know if you want to call you professor, because